Usual is that all my neighbors' yards are covered in snow, but for some reason mine has no snow on it at all.
Oh, that is interesting.
It's because my kids shoveled it all into a pile.
Oh. Yeah.
Just have to convince them to do it when it's useful.
All right, so let's pick up where we left off. We were deriving the matrix form for this method. So let's continue with that. I think what I want to do is let's do one of the terms and then write down the remainder so you can kind of see how, term by term, if we look at our weak form, we've got that, let's see. Okay, so we've got our weak form. It looks like the following. Let's remind ourselves of what we're doing here. So we've got an integral over omega c. In this case, it's just 0 to L. It's just a one-dimensional guy. And it's delta u comma x h. I guess I should say this is the Galerkin form. EA u comma x h dx plus delta u h evaluated 0 lambda h minus c delta u h f dx minus delta u h evaluated at L h L. That whole thing has to equal 0 for every one of these tests, every one of these delta u's. That's our first equation. Then our second equation is that delta lambda h, a value applied to the constraint uh evaluated 0 minus u naught, has to be equal to 0 for all delta lambda h in the real numbers. Okay, so let's go to the matrix form now. Let me just do one term of this. Let's take this guy here, the strain energy term. And so what we do is, because we're in the Galerkin setting and these are all discrete, we can write down that UH is, let's make sure my notation is consistent. The UH, let's take a sum on B, dB, NB. This is going to be over the flex domain now, okay? And then we have that delta UH is going to also be written as a linear combination of CA and AF. And we have our Lagrange multiplier is going to be, let's say it's the n plus first, we'll just append one basis function to model the Lagrange multiplier. And then we've got delta lambda h, which is delta lambda n plus 1, n of n plus 1. Now, remember that this is just a one-dimensional problem where we have our flex domain, and then we've got our computational domain embedded inside of it. And we're enforcing the constraint u naught at 0. So really, this is just a number. It's just a single parameter that we're going to be solving for, the Lagrange multiplier. And so really, we can model this by just setting this basis function equal to the constant 1. Okay, now what we do is for this term up here, we're going to take this guy and plug it in here. And this guy, plug it in here. So let's go ahead and do that. And notice that these basis functions are defined over omega f, but this integral is written in terms of omega c. So there's a little bit of modeling there that we're going to do. So we're going to rewrite the integral over omega f and then introduce what we call an indicator function. That's going to segregate out points that are in the CAD domain versus points that are outside of the CAD domain. So it's going to take points x and return 1 or epsilon. And then where we see delta u h comma x, we're going to write the sum on a, ca, and a, f. And this is going to be comma x. So that's one substitution. And we've got our second substitution, which is the sum on b. Let's see, d, b, and b, comma x. Notice the derivative just passes through to this function, the basis function. This is just a constant value, the coefficient. And then we've got dx. What we can do now is do a change of coordinates, just to simplify the integral a little bit. So if we do a change of coordinates, we're going to pull back to the parametric domain. So we're going to go ahead and use our change of coordinates function and pull back to omega hat f. So we end up with the following: omega hat f. And well, actually, let me just to compress things down a little bit. Let me not make another line here. So this is omega hat f, and then this differential needs to become dx dxc dxc. All right, so let's remember that this integral is actually what we call a bilinear form, which means that these sums can actually come outside the integral because it's linear. And so let's go ahead and make that change. So why don't we pull out the, let's go ahead and pull this guy out here first. Take this guy and we'll pull him out. So we have a sum on a, ca. Okay, now we can also pull this sum out. So let's go ahead and do that. This guy. Kind of getting a little squished over here. Let's move this integral over. Sum on b and integral. Let's put the dB over here, and it'll become clear why I'm doing that in a minute. Okay, now this whole thing has to equal 0 for all possible coefficients CA in the reals. Okay, and because these CAs can be these guys can be non-zero, then we know that this guy inside the parentheses, inside the brackets, must be equal to 0 for every index A. And so that's going to give us our n equations. You're going to have one equation for every index A. So A equal to 1 is going to give you an equation, A equal to 2 is going to give you an equation, and so on. And so that's how you go from this continuous setting to your discrete matrix vector format. It's this step right here where you notice that this condition holds here. So what we do is we simply erase this sum, these brackets, and then we transform this to comma a equals 1 to n. So now we have n equations. Now let's just take a look at the structure here. I'm almost done here, and I'll take some questions. I know this is kind of going on and on and on here. So we've got, let's put this in brackets now. Okay. So now what you should see is that what's actually popping out here is a matrix times a vector. If you look at this sum, so we have n equations. So let's take a equal to 1, for example. Okay, so the first equation, this thing is going to become a 1. And then we sum over b. So this is actually an inner product of the 8th row and all of the unknown coefficients db. So this is going to be, the sum is going to be b equal 1 to n, where these now are going to run from 1 to n. And so so you get this inner product of this guy, this matrix vector product of this matrix times the d vector. So what we often do is, let me move this. And so what this, let's go ahead and write this down. This is going to give us the so-called stiffness matrix, where we're going to have K is equal to a matrix. The A-bth component of that matrix. So the A-bth component is this thing in brackets, right? Here's the A index and here's the B index. You evaluate that integral, it gives you a number, and you stick that number in the matrix in the A-bth location. And then the vector D, it's just D1 through Dn. And that's the unknowns that we're solving for. Okay, so that's the first term. That's this term up here, gives us a K matrix. The given quantities, so here's our body force. Here is our traction force. We will normally go ahead and subtract these to the other side of the equation, and then these will generate our force vector. And then we have the equations coming from our Lagrange multiplier. So let me put that all together, and then I'll pause for questions. So what we end up with is a matrix, a block matrix that looks like this. Okay, where this guy here, this is often called the constraint matrix, is going to be this term here. And if you notice that it's going to end up looking like n plus 1. And then this is going to end up with a n b f sum on b again db. And then you're going to, this is known data that's going to go to the other side. So this equation will look like then n n plus 1 u naught. That's what ends up. Delta lambda h times u naught is this right here. And so this is what we call the B matrix. In this case, it's not a matrix. It's actually just a transposed vector because there's only one Lagrange multiplier. So if you had multiple Lagrange multipliers, you would have one equation for every Lagrange multiplier, and that would create a whole bunch of rows. But again, you're still multiplying the columns, the B's are the columns times your D. So it's B times D. It's just like you would expect from the matrix that we wrote below. Zoom puts things all over the screen. It's so obnoxious. Always in the wrong place. Okay, so that's the basic idea where when you go from the Galerkin to the matrix form, you plug in your discrete expressions for your trial solutions and your test functions, and you go ahead and segregate out the unknowns into a matrix vector format. And this is what the matrix vector format looks like in this case. Okay, that was a lot. So let me pause and take any questions before we move on, if there is any.
Could you just say again what the K was?
This is called the stiffness matrix, and it is equivalent to the entries of K are coming from the things in the brackets here. It's the evaluation of these integrals.
Thank you.
Okay. Any other questions? It's hard for me to believe there's only one question on this. So everybody's got it.
For me, it's just so much to take in that I can't come up with a question. So
Okay. Yeah, this subject has to be wrestled with. Yeah, it's hard to get much from lectures sometimes. Okay,
so Dr. Scott, I have a quick question.
Yep.
So last time we had this indicator function, but I don't see the indicator function in here anywhere.
That's right.
Oh, okay. Sorry, okay, never mind. We're good.
Yeah. So this indicator function is basically segregating points. So as you go through the integral, you plug in the value of x, and if it's inside omega c, then this evaluates to a 1. Otherwise, it evaluates to a very small, theoretically it evaluates to 0, but we set a very small parameter to regularize it, so we don't get too poorly conditioned stiffness matrices.
So have we not left because you're saying you're at omega hat f in this right here.
Yep.
So have we already applied the I don't remember what we called it, like conversion?
The change of coordinates?
The change of coordinates.
Yes, I've already pulled it back. That was one of the first steps that I took. Was I originally wrote down the actual integral in physical coordinates in terms of the geometry omega c, and then I did a change of coordinates to this parametric domain, and then took it from there. Okay, give myself a little room here. There's a few things I want to tell you about. All right, so first, let's talk through what's happening here. So what we're doing, we're integrating down here. Okay, so we're integrating all these points, every single point. We take an xc point, we map it through x sub s, f, into a corresponding x point. And if the x point is here, what would happen to the integral?
It would be 0.
Okay, it would theoretically be 0. We, of course, let it be some small value that we put into the stiffness just for regularity, but essentially it's 0. because it's outside of omega c. Then we keep sweeping through all the points, and eventually we get inside of omega c. So maybe we're at some point here. We map that point through x of f into omega c. This then evaluates to 1. And now we take our flex basis functions that are defined over the entire domain, but we're really only evaluating them inside of omega c. And we go ahead and evaluate this integral. Let's talk about these quantities here. Let's first start with this here. dx dxc. This perhaps more appropriately could be written as it's really dxf, because that's how we're computing the x quantity, x coordinates. Okay, so that's this guy, this Jacobian here. So how am I defining this mapping? Do we recall how this mapping is going to be defined? We make the decision, right? So far in your homework, you've hard-coded in just a linear function, but we want to move away from that to a more generic representation of our geometric map. So does anybody have any thoughts about perhaps what's the right way or the most convenient way to do that?
Like a Dirac function
Okay, well, you're on the right track with
or Heaviside?
choosing some functions. We're not going to use the Dirac delta function. We're going to use another function other functions we have laying around in the flex domain. Why don't we just do this? X of f is equal to the sum of coefficients times our flex basis in the parametric domain. Why don't we define it that way? Why don't we just define our geometry as a linear combination of, these are called nodes, or in the CAD world, they'd be called control points. We choose some points, some x values. We multiply them by our basis defined in the parametric flex domain, and we allow that to be our geometry. So this is what is common. This is just an isoparametric kind of idea here. But notice that something very important is happening here. We're using a common isoparametric mapping in terms of our basis to define our flex geometry. But our CAD geometry, right? Our CAD, let's say we have a omega hat C. The actual mapping into our CAD geometry, we go ahead and leave completely unspecified, except for this indicator function. So the only question that we need to answer about our CAD geometry at this point is whether an x value is inside the point, inside the CAD geometry, or outside of it. So this is a very strong and important decoupling of geometries. We essentially have a flex geometry defined through this mapping that we control, and a CAD mapping that we don't know very much about, and it could be a total disaster, a total mess, and not suitable for simulation. But as long as it can answer this one question here about point inclusion in inside-outside test, we can go ahead and use any CAD geometry we would like, or any geometry description whatsoever in this formulation. And so this is kind of, when we use the term isogeometric, and we put it in quotes, meaning it's just kind of off the cuff, you could make an argument that this is kind of an isogeometric method because of this decoupling of the geometry, and we can use the exact geometry without transforming it in the simulation. Okay, so let's see. Right. So let's just step back for a moment and just examine this mapping here, because I taught this enough to know that even though everybody is quiet, there's, like Rebecca said, well, you might be so kind of, it's so new you don't even know what to ask. So let me dive into some of the basic details here.
Can I just express like something that's confusing me?
Sure.
So when we are computing, the FEA equation or whatever it is, we're like when we did that one algorithm and we were doing it for sine, right?
Yep.
Well, when we were doing that, the sine was both representing our geometry, the physical.
Nope, the sign was never representing the geometry.
Well, so what was representing our geometry?
It was the 1/2 1 plus xc. You
Well,
wrote
that was the
that's-
conversion.
Nope, that's the change of coordinates, but
The change of coordinates.
But it's defining x. It's defining the geometry. This was the geometry of that simple problem that you guys worked in the notes.
Well,
this
so
right here is xf. You just wrote it down as being a linear function, but that is the geometry. Let's look at this. Okay, this is what I wanted to, I know this is a point of confusion, so let's write this picture a little bigger and dive into the details a little bit. Hopefully, Eric, it'll help you visualize this a little better.
Okay.
Well, so you're using geometry to mean two different things here, right? Because you could also say that the geometry for that problem was 0 to 1, right? Because that's the analog to the CAD geometry for that case.
Yeah, so there's, in this case, that's what we need to talk about. There's, and I'm actually doing this on purpose because this is how it's talked about in finite elements, right? This mapping sometimes is called the geometry, sometimes it's called a change of coordinates, sometimes it's called the geometric mapping, sometimes it's called a parametrization. But the point is there mathematically, it is really the mapping from some parametric domain into the physical coordinates. We call that geometry. So let's dig into this. So let's just first talk about this guy here. Okay, and let's say there's some sorry. So why don't we, from this time forward, why don't we call this, I think the best way to talk about it is to call it the geometric map. And then we'll call, so our precise description of this will be a geometric map. And then when we want to talk about it kind of shorthand, we'll use the term geometry. Is that okay? And I'll be consistent from now on. Okay, so the geometry or the geometric map always takes some parametric domain with coordinates xc into some physical domain with coordinates x. And so you can see that this is a well-formed geometric map because it takes coordinates xc into the x coordinate x. Okay. So this, let's just write down a few of them. Okay, so let's say, let's erase this particular instance. Now, the point I'm trying to make that I find, I know it was for me, it was difficult, and I've seen it to be difficult for other students as well when they learn this subject, is I write this arrow, and this symbol here, this is our geometric map. And now we can define it to be anything we want, right? I mean, there will be some conditions on that map that I want to discuss later, but for now, let's just use our imagination and kind of visualize what this map does. Let's say, just for fun, that this domain goes from 0 to 1. And let's say, just for fun, that this domain goes from 0 to 1. Doesn't have to. They can be different, have different limits. Now, let's just throw out some x's, some maps. Anybody have a favorite map that they want to share? Probably not. Huh? One you've just been thinking about, maybe at breakfast this morning.
0.45.
Yeah, identity would work here, right?
Yeah, why don't we, that's, there you go, Ryan. Let's just do this. Let's say that our map is just that. Do you see what that's doing? It's simply taking some xc value and assigning the coordinate x to be that xc value. Okay, let's talk a little bit about this map. What are its properties? As a function of xc, what is this? Like, how would you describe this function of xc?
It's C infinity.
Okay, it's c infinity. Okay, so that's the continuity level. Is it a polynomial?
Yeah.
Yes.
And it's a linear polynomial. Okay, great. Now let's examine linearity a little bit. Linearity means, in this case, that there is a nice correspondence between the distribution of coordinates in the parametric domain and the distribution of x coordinates in the physical domain, meaning that there's not going to be kind of a stretching of the domain in any particular direction. Every point maps directly onto a corresponding x value, right? So if you took, let's just to be concrete, let's pick 3 points to kind of experiment with. Maybe we'll pick, yeah, let's go ahead and make these a little more concrete here. So let's call this guy maybe, I don't know, 1/4. Let's call this guy 1/2. Let's call this guy 3/4. And let's just kind of watch how these points are mapped into the physical coordinates. And this tells you a lot, because this mapping is very important in everything that we've been doing. So understanding its behavior is critical to understanding actually what our method is doing. So if xf is equal to xc, then we know that x0, let me go ahead and erase this. Let's see, we've got, maybe we call this x0, x1. Okay, so what's x0 going to be according to the current mapping that we're using?
1/4.
1/4, 1/2, 3/4. Okay, great. Now, so that's a very nice one. And so Eric, basically the mapping that you hard coded was 1/2 xc plus 1. It's nothing more than this mapping with a couple of constants to allow the endpoints to not be equal. Does that make sense? Like you can go from -1 to 1 with this guy, but it's still a linear polynomial. So it has this nice distribution property where the structure of the parametric space is preserved in a linear way through the mapping x. So that's nice. Maybe we pick the next one I wanted to look at just really quickly here was one we did before. Let's say it's like c cubed. All right, so it's still c infinity, but now it's a cubic polynomial. And so let's go and move our points around accordingly. Okay, so if the mapping is a cubic polynomial, where does 1/4 go? What does it map to?
0.016.
So it's 4 cubed, right? So it's 1/64. 0, 1/64. And then this goes to 1/8, right? Which is maybe and then 3/4 goes where? 27/64. Is that right? So not quite halfway. Okay, so you can see that the distribution of points is following the shape of your parametrization. Okay, so now why is this relevant? Like why do we care about this? Anybody have any thoughts about, like, why wouldn't we just always use this map for everything? Every possible finite element simulation done in the world, why can't we just use this mapping here?
We may care about a certain portion of the domain more than we care about others.
Okay, so maybe we can use the geometric map to kind of emphasize certain parts of the domain. That's one point. What else?
It might not fit the geometry as well.
Yeah, exactly. This is defining geometry, right? So it's saying I have some domain and I'm mapping it into some shape, right? That's what these maps do. Not every shape of interest can be modeled with a linear polynomial. Like those of you who are in industry, you're working with very complicated CAD. So your mapping to capture the geometry in the simulation needs to be sophisticated. So the most common kind of pragmatic approach to this problem is, rather than using these extremely simple functions, which really they're really just academic exercises to give you some idea of how this works, we're going to use this idea up here, okay, where we take a linear combination of our basis functions times nodal values, which are defined up here. And so what is this? What's the advantages of using this kind of geometric map in terms of a basis that we control?
Simplifies the function, right?
Yeah, so it standardizes things, right? It means that as soon as you define your finite element basis in the parametric domain, then all that's left to define the geometry for your problem is to select the nodes. That's nice. That's kind of a nice, that's like a machine, right? It's not like you're guessing or picking. You're just picking an approach that you use in every case. So if you had linear polynomials, for example, as your basis functions, then you would pick nodes, one node for each linear basis function, and it would generate a linear map that would create some geometry here. Okay.
So remind me, on that equation, you have xf and you have the sum of x sub af. Which one represents your c?
Yeah, so this,
selecting your,
so the function, the basis function is gobbling up xc, and then it spits out an x after you multiply it by the nodes. So then the c goes in there, and then out comes an x.
so in terms of this, if you know your x and you select your nodes, then you're solving for what your basis functions will be. Is that correct?
No, you specify your basis. Okay, you choose the basis functions, and then you run a mesh generation procedure to generate the nodes, and then you simply follow this recipe to generate your geometric map. So let's just do an example. Let's say, let me get rid of these specific. Okay. Let's say you
So I guess what I'm kind of getting caught up is that when you're saying you select your nodes and then you pick a basis. So if I have a whole bunch of nodes that I've stuck out on a surface, and if I don't use a linear basis, right? So like, for example, traditional FEA, I'm going to use a linear basis, which means that when I select my nodes, it's a straight line from one node to the next. And you basically have no definition of what's going on in between those two nodes. So you lose all of that information. But if
no, you have it, it's linear because your basis tells you exactly what the geometry is doing between those two nodes.
Well, if you're using a linear basis, then you don't know anymore. Like,
yeah, you do. You know it's a straight line. You
well,
know
You
all
just
of
don't
them.
have a degree of freedom for it to do anything other than go in
Yeah,
a straight
it
line.
has to
what
be a
I'm
straight
saying
line.
is if the original geometry was not a straight line, like let's say we're looking at a circle, right? And you pick 4 nodes on that circle. Well, now it looks like a diamond. And the fact that the original geometry was a circle kind of gets lost in the math because you used a linear basis.
So
But if
in the
you use a
language,
higher,
Lost in the approximation.
that's what normally happens in finite elements, right?
yes, exactly. So
Yep.
if
Because
you
you
didn't,
throw it away. You throw in normal finite elements. Let's say you have a circle. That would be what we would call omega c,
mm-hmm,
the circle. In normal finite elements, what you do is you replace, you say, I'm going to replace omega c by the geometry created by this mapping, regardless of how accurate it is. And then this omega c is gone forever.
yes.
In our approach, omega c is still exactly represented in the model.
See, that's where I'm losing you, because if this equation is what we're using, then that's not what it's telling me. What it's telling me is you're still getting lost.
No,
Because-
you're not. I'll show you. And let me show you right now how this
Okay.
works. Okay. Because this is like the whole point of what we're doing here. So let's add a little more here. So let's say we have our geometry. Let's say our circle is a line in this case. Okay, here's our geometry. Here's omega c. Okay, so there is some mapping, let's say, somewhere. We just don't have it, or we don't know it, or we don't like it, one or the other. Usually it's just so poorly defined that we can't use it for simulation. So let's say so this is our CAD, this is Eric's circle. He says, well, we lose the geometry in this method. So let's talk through why we do not lose the geometry in this method. We define some overlay flex geometry on top of omega c. We know omega c. In other words, I know if a point is inside of omega c, I know it. So if I evaluated an infinite number of points, I would return the exact geometry. Do you agree with that, Eric?
Yeah, as long as you have omega c. Yeah.
Okay, so our finite element method started out like this. Delta UH, comma X, EA, UH, comma X, EX. Okay, and then we went through that exercise of simplifying it, and we get that every entry of our stiffness now looks like this. We're now switching over to the flex parametric domain. We have this indicator function. N-A hat F, comma X, E-A, N, B hat F, comma X, DX F, DXC, DXC. Okay, so now the question that I'll pose to Eric, and if it's open to anybody, is why don't we lose the geometry? Where is the geometry in this problem?
So the geometry is inside of your flex domain. That's one of the requirements, is that the mesh that you create has to be bigger than your actual CAD geometry.
Yep.
So then you've got a mapping from parametric coordinates to physical coordinates that includes real space, of all of the CAD plus a little bit.
Yep.
So you can always get to a point that's on the CAD that way, and you don't have to make the you don't have to throw it away like you would in traditional finite elements with body fitted mesh, because it's not body fitted, it's a little bit bigger, so it includes it all. And then the only thing that you need to say whether you're in the CAD or not is the indicator function.
Yep, that's right. So the circle, Eric, is right here. That's where that's where the geometry. See, we don't need. Notice what we've done. We say we don't like the CAD parametrization, like the mapping, but we know where the CAD resides in physical space. Like we know what the actual geometry, all the points that are inside the CAD, right? That's what you see on a computer screen, for example, the points.
Yeah.
Okay. So what we do is we say, well, I either don't know this or I don't like it. So why don't I overlay another geometry that I do like on top of it and that I control? And then notice that everything in here, this is actually with respect to X, big XF, right? These derivatives. So everything that has like either a differential with respect to one of the geometric all the mapping information, now we've swapped out this guy for this guy. And then we solve the problem in this more generic format. So we've decoupled the CAD geometry from the mappings that we're using to compute quantities. So we may have a basis. Let's say we have a basis, right? Here's our flex basis. I don't know, maybe it looks like this, something, whatever, I don't know. Okay. We're still solving our physical problem over omega c. But the functions that we're using, these NAs, are the restriction of the flex basis functions to omega c, right? Because if it's outside of omega c, it's 0, right? So we don't even see the functions. So we take these functions here as our basis, which is perfectly acceptable, right? This is a perfectly acceptable set of functions that you can approximate a solution with over omega c. The parametrization of those functions, though, we control through this mapping. And this mapping is much more generic than X sub c because it can totally subsume the geometry, and we can make it as simple as we want, right? Or as complicated as we want. And that's the whole point. With splines, you can chop functions off like this and still get good behavior, good, accurate, converged solutions with these independent geometry parametrizations. Okay, so that's the whole idea behind this thing we're calling the flex representation method, is this idea that we decouple, which isn't new, but the way that we decouple, this right here is the new thing, right? Because normally these immersive techniques, they still specify these to be very simple functions. And we're not doing that. We're actually writing our flex parametrization in terms of a higher order spline basis. And that's what's new here, is this is the key to making it completely general and flexible and applicable to very complicated geometries and still preserving. So this is really this is the big point right here, is that this is what we choose to do.
Those NAFs are the portions that you just are those those bases, that new basis that you just chunked out.
Yep.
And the X's.
And then these guys, these are just nodes, so you just pick some points right along in the domain, in the flex domain. So this would be like x1, x2, and so on. Multiply it times your basis defined down here, and that generates the parametrization for the flex geometry over which you solve the problem.
Okay, so those NAs with the F superscript aren't limited to just inside the box.
Oh no, you define them on the flex domain, but we solve them as if they were restricted to the CAD domain through the indicator function.
Yeah, okay.
Okay, so this has significant implications. The fact that this isn't a simple function is what differentiates the flex representation method from every other immersed method that I'm aware of. And we'll talk a little bit about the implications next time in terms of moving between these domains, because we have a few more terms. We've just really talked about the stiffness, but I want to talk a little bit about how we handle boundary conditions and other quantities using these maps, and that will complete the picture for this method.
So the answer to this might just be for another time, or I can call in another time to not interrupt the class, but I still am a little hung up in how if you have picked your points with XA and you arbitrarily pick some bases, if you don't fit that function to your geometry using some sort of, fitting algorithm, how does it then know what the original geometry actually looks like?
The indicator function. This function right.
But the indicator function is just a series of points.
It says every point that's inside the domain.
Well, then you would have to have a function that is just as complicated as your original omega c, but we said we didn't like that. So if you're trying to simplify omega c by points, instead of having a continuous function, then...
No, here's the thing, Eric, is that the indicator function is just a function of x. It's not a function of any parametric coordinate. So all I need to know is the positioning of the geometry in physical coordinates. I don't need to know anything about the parametrization of that geometry. That's the key. Because I'm using a different parametric domain. I'm parametrizing my solution in terms of a different parametric domain than I am the geometry. So there's no such thing as fitting. The fitting actually will happen automatically through boundary conditions, and you'll see it a little bit more next time. But yeah, I mean, it is not, it's just a generalization of standard. What you describe right there, Eric, is what we call isoparametric finite elements, where we say, okay, I want a parametrization of the geometry. I'm going to simply set it equal to x sub f. And if it's good, if it's a good approximation, that's fine. Then if you say I want x sub f equal to whatever x sub c was, then you have to solve a problem for the x sub a's. But that's not what we're doing. We're not coupling them in this way.
Hey, Eric, I wonder if because I'm starting to realize something that maybe if you missed it, then it might help you to realize it too. Everything's inside like a domain. Like if we went with that circle, you stuck it inside of a box and said this box is the entire domain. And we're going to just find little points anywhere in that box. And one of the points might be inside that circle. Or I guess it's a sphere in a box, right? So, because this isn't just saying we're going to figure out what the sphere looks like. We're just going to figure out what the box looks like do the equations on that box, and then inside it is a sphere. And if the points that we're looking at are inside that sphere, because this is immersed, this isn't body fitted.
Yeah, I understand that. We'll have to talk about it later. I don't want to interrupt the class anymore.
Okay.
Is it, I don't know, is this maybe getting into like quadrature? Like if you don't have a high enough
Yeah, quadrature.
number of quadrature points to capture the
Yep.
discontinuity when you're
Yep.
going.
That's right. So that's exactly right, because when you multiply by this indicator function, what are these functions really doing? As they go here, they then get really small, right?
Mhm.
And so there's, if epsilon is really small, but it's still bigger than 0, then what's happening in these integrals is you have some value, maybe it's magnitude 1, right? And then the quantities smoothly vanish to something of order epsilon. And that's the key, is this smooth transition means you won't disrupt the convergence rates. But of course, you need a quadrature scheme that can accommodate these transition regions, which is something we'll talk about.
That seems like that's why regular immersed methods might not work if you don't.
Yeah, so with regular immerse, that's right. It's this smooth transition into this flex domain that gives this method, the precursor where you have simple mappings is called the finite cell method. And it's one of the real attributes of value here. And so using splines is essential, because you can imagine if you were using the derivative of linears here, you get some pretty nasty discontinuities that would be difficult to capture.
Yeah.
As far as accuracy is like the quickness with which you get down to 0, like, is that kind of what affects your error? Like how quickly you can...
that will affect the error. Yep, the size of epsilon is an important parameter that you need to control. We sometimes call it a penalty. So it's serving the role of a penalty in a
that's interesting.
method. Yeah, so this is just good. You've got to dive in and try and work the problems and try and just hammer this into your brain. It's not going to come in a lecture. It's going to come, you have to have some aha moments as you struggle with the material.
Dr. Scott, I have a quick question. So, when we are doing at core form, when we are using the flex method to do body fitted mesh, then XF is only approximately equal to XC, right? Because the parametrization that we are using is still different, right?
That's right. In practice, when you do the solution procedure, you never get exact equality, right? It's always an approximation.
Yeah, and that is not that is not what conventional isogeometric analysis is, right? I mean, conventionally people don't do that in IGA, right? Because people say that we use the exact same parameterization.
Yeah, and that's why nobody can do any real problems.
Right.
With this is because the only way that this would work is if your CAD was reformulated in terms of functions that always generated these mappings that were consistent with simulation. And that's just never going to happen. And so we're taking a more, what I would say, we're returning more to the roots of isogeometric methods, in the sense that it's all about overcoming the mesh generation procedure and having a way of incorporating the exact CAD. It doesn't mean you need the exact CAD parameterization. It means you need to be able to get to the exact shape of your problem.
Mm-hmm.
Yeah, and this is the way the whole field is moving. So it's not just me like coming up. I mean, this is built on, obviously a huge body of research that over time there's these trends that emerge, right, as best practices, and this incorporates a lot of those as well.
Mike?
Yep.
When doing your flex domain, why are use splines necessary? Why couldn't you use
Okay, that's a great question. Okay, so this is a little bit more advanced, obviously. I'll jump a little bit ahead. Normally, this mapping is some affine mapping. So in traditional immerse techniques, we get rid of this and we replace it essentially with what Eric described at the beginning, some function, no, it's some function of some let's just notation here. It's going to be an affine mapping, so it'll be some scaling, rotation, music C plus some. So it's an affine map, okay? That's traditional immersed. Okay, which means, again, the problem is let's say you have a really complicated, this is obviously not it, but let's say, yeah, this is your geometry, okay? This is complicated, although we all know it's not. But that means you're always, since your parametric domain is always some square of some sort, and you're just doing an affine rotation and translation of a square, you're always kind of stuck with immersing every possible CAD that you could come up with in a box. And so your basis functions are defined over this grid. The problem is that you incur, as Ryan correctly pointed out, there are, like, I would say, weak discontinuities in these elements that you have to capture through quadrature, and you engender an error, right? With enough degrees of freedom, you're going to converge. But in the pre-asymptotic setting, where you have a limited number of functions, you're going to incur an error, and that error is going to be proportional to how poorly fitted the flex geometry is to the CAD. But if the flex geometry can only be an affine mapping, then that kind of means you're stuck with regards to the error that you engender. It's always going to be this case. So what we're doing is what I believe to be the important step here for real problems is we say, okay, let's not restrict ourselves to affine mappings, and instead allow this to be a very rich spline object written in terms of control points and spline basis functions. But now the basis functions that we use, namely U-splines, which we haven't talked about, are general enough that we can create, like, if let's say there's a whole bunch of little holes in here, you know, we can create an overlay grid that is much easier to generate than maybe the original CAD, but has a parametrization that still closely follows the original geometry. And so that allows us to immediately make methods that are very competitive with body fitted splines, but much easier to go through the model building process, because now we have this much richer space. And U-splines are the only spline technology that allows us to build really high order, smooth, unstructured, volume, surface splines over CAD. So it's really the only game in town right now that we can do this with, right? Because normally higher order smooth splines are always just mappings of boxes, you know?
In the limiting case, your affine mapping will still converge.
Yes, it will still converge, but it's going to be orders of magnitude, you know, compared to the flex methods we're going to be considering, we're talking about an order of magnitude difference in degrees of freedom required. So, and, you know, like, as an engineer, like, this just doesn't, I just don't like immersing things in boxes, because it's just, like, you think about load paths and all those other kinds of considerations about structures, you want the parametrization or your basis functions to somehow be aware. And that awareness makes these methods more accurate than body fitted linear, tet or hex or quad, tri, and almost as accurate as body fitted higher order splines with none of the complications of model building. So U-splines are the only game in town that gives us that. There is really only one spline technology that is sophisticated enough right now that allows us to build these mappings, and that this set is rich enough to allow us to kind of tailor it to anything the problem indicates would be appropriate. So that's the idea, Curtis.
So in practice, it's really a consideration of efficiency for your quadrature.
yeah, I mean, we want to build models fast, we want to iterate quickly, and we want to preserve higher order accuracy and robustness. Yep.
Mhm.
Which is always the game. That's the game with every numerical method. You can solve anything if you have infinite precision, right? With the dumbest method in the world. Just sample anyway. Yeah. I mean, the numerical methods are all about efficiency and robustness. Okay, that was good. Yeah, I'm learning as I present this, like how to talk about it. It's yeah, so I appreciate the opportunity to teach it. Any other questions? Okay, well, let's stop here. Thanks, everybody. See you on Wednesday.
Thank you.